After studying this module, you shall be able to know how to assess the statistical significance of a correlation coefficient and evaluate the significance of correlational differences in two independent samples and evaluate the significance between correlation differences in two dependent samples. Introduction. In behavioral science, research often entrusts itself with understanding the relationship between two or more variables. The readers have an understanding of the Pearson's product moment correlation. We have done it in previous modules. If you don't have an idea about it, please refer to those modules for it. The correlation coefficient R, that is the measure of Pearson's product moment correlation, it provides a measure of degree and direction of relationship shared by two variables. Covariance is a measure of the extent to which the two variables vary together, and using the two we can find the value of correlation as R is equal to covariance between two variables divided by standard deviation obtained on one variable multiplied with standard deviation obtained on the second variable. Just the way two means can be compared for their differences to be significant or not, or a single mean is different from the population mean significantly or not, the correlation coefficients can also be tested for significance. After establishing a relationship between the two variables or measures through correlation, the next inquisition is to know if this correlation coefficient that one has obtained is significant enough or not. Or one may say that it may be because of sampling biases or sampling errors that you have accidentally hit upon a relationship. One can test that an obtained correlation is different from the no correlation state to such an extent that it can be referred to as significant. Similarly, when comparing two measures of correlation coefficients, can they be so different that their difference is significant? The current module aims to understand and interpret these relationships and their applications to the research data. The module explores the statistical significance of a correlation coefficient and the difference between two correlation coefficients from dependent and independent samples. The statistical significance of a correlation coefficient. The correlation coefficient. Although the Pearson's correlation R gives a very robust measure of the relationship between the two variables, a researcher may still like to know if the relationship reported by the coefficient exists in the population or it is just a result of mere sampling errors. Let us take an example of two variables, IQ and income, which may be positively correlated, and the researcher would like to know if this result is not due to sampling errors. So, to prove his point and check whether it is correct or not, the data was collected on a sample size of 5 and the correlation was found to be 0.956. The level of significance on which the data would be tested is 0.25. The steps in the significance are: the steps involved in testing the significance of correlation coefficient are as follows. First is stating the null and alternative hypothesis. The null hypothesis states that there is no relationship between the two variables. In other words, the research sample is from a population that exhibits no correlation among the variables. Like in this case, we have taken the variables of income and IQ. So the population should not show any relationship among the variables. The frequency distribution of correlation R is roughly normal in shape, and also larger the sample size chosen, closer the sampling distribution of correlation is to normality. So one must prefer a large sample size if one wants to go for checking the significance for a greater reliability of results. The null hypothesis is stated as HO is equal to rho equal to 0. That means there is no correlation among the chosen variables in the population. The alternative hypothesis may be, in case of non-directional hypothesis, rho is not equal to 0, and in case the researcher is interested, he can go for directional hypothesis too. Computing the t-value is the next step in the direction. The significance of Pearson's R is tested by calculating the t-value with degree of freedom of n-2. Remember, we have two samples here, that is two variables from which the statistic have been obtained to calculate correlation. So the df would be n-2 here. The formula used for the purpose of calculation of t-value is t equal to r into square root of n-2 divided by square root of 1 minus r square, where r is the obtained Pearson's correlation coefficient, n is the number of pairs of x and y. Upon substituting the values from the example mentioned, the t-value can be found easily now. T is equal to 0.95 into square root of 5 minus 2 divided by square root of 1 minus 0.95 square, which turns out to be, after calculations, as 5.23. Now we have a t calculated value, and the job is simple. We need to compare it to the critical value of the t which is mentioned in the student's t distribution table. Now, to obtain the critical t value from the table of students' t distribution, we calculate and compare the t values and arrive at a conclusion. For DF3 and for a two-tailed test, the t critical value for alpha 0.05 is 3.182. As the calculated value of t is more than the critical t value, one rejects the null hypothesis of no difference, that is rho equal to 0. In other words, the relationship between the income and IQ is not because of sampling errors, and it exists in the population. The significance of the correlation can also be tested using the Z statistic. However, we shall not discuss this in detail here, but the equation is as follows. Z is equal to r dash minus rho dash divided by square root of 1 upon n minus 3, where r dash is the Fisher's transformation for the sample's correlation coefficient, and we shall see that Fisher's transformation in the coming sections of the text. Rho dash is the Fisher's transformation of the population, and n is the sample size. After calculating the Z value, it can be tested for the significance the usual way. During the behavioral research, it becomes useful if one can also compare the two correlation coefficients and know if they are statistically different. Statistical tests are available to facilitate this. A difference in the method does apply for the independent and dependent samples, and we shall explore both the samples differently in the subsequent sections. The coming sections discuss these methods to study the statistical significance of difference between two correlations among dependent and independent samples. Studying the statistical significance of difference between two correlations for independent samples. What are independent samples? Independent samples are samples selected from same or different populations which have no effect of each other. No correlation exists between the samples. The outcome for one sample is assumed to be unrelated to the outcome for each of the other sample. Or if the outcome for one sample is known, it will provide no information about the outcome of the other sample. For instance, comparing males and females as two independent samples within a population to compare a treatment group to a control group in an interventional study, making a comparison of correlation coefficients. When there are two correlations that come from different samples and are independent to each other, it is a two independent correlation study. For instance, if one wishes to know whether height and weight are correlated in the same way for two distinct social groups. X and Y could be seen as representing height and weight for the first social group, and A and B could be representing it for the second group. Thus, there are no overlapping correlations and hence no dependent correlations with focus on an independent significance test. When conducting correlation analysis by two independent groups of different sample sizes, typically a comparison between two correlations is examined. It is recommended when the correlations are conducted on the same variables by two different groups and if both correlation coefficients value are found to be statistically significant. This is done by transforming the correlation coefficient values or the R values into Z scores. This is the Fisher's R to Z transformation done so that the Z scores can be compared to analyze for statistical significance by determining the observed Z statistic. With the observed Z statistic, that is Z observed at a set alpha level or the level of significance, the statistical significance can be assessed. The pictorial representation of the steps is given here and we can just read them, and the steps are that first we run correlational analysis between two independent groups and determine the correlation coefficient. Next, write down the sample sizes per each independent group and then using statistical chart with Z value, determine the Z value of Z1 and Z2 corresponding to the correlation coefficients of R. This is by Fisher's Z transformation using the following equation as Z is equal to R-1 minus R-2 upon square root of 1 upon n1 minus 3 plus 1 upon n2 minus 3. Once the observed Z value is determined, we assess the statistical significance by checking if the observed value is greater than the critical value. If the observed Z value, that is the calculated value, is equal to minus 1.97 and the level of significance is set at 0.05, which indicates that the critical value is plus minus 1.96, the observed value of Z is greater than the critical value, implying that Z observed falls in the rejection region and thus statistically significant correlation is there. Assessing the significance. For the independent case, the Fisher's Z transformation for correlation coefficients followed by testing of the null hypothesis rho 1 minus rho 2 equal to 0 using the student's t-test. Let the null hypothesis be represented as HO is equal to rho 1 equal to rho 2. That is, the two are equal or the difference between them is 0. If one wants to test the correlation between X and Y in another population is the same as the correlation between X and Y in this population, one can use the procedure developed by R. A. Fisher in 1921. For each of the two correlation coefficients, transformation is done as R dash is equal to 0.5 log of 1 plus R upon 1 minus R. Then the test statistic is computed using the Z equation given here and the probabilities obtained thereafter from the computed Z. For example, the relationship between misanthropy and support for animal rights was compared between two different groups of person to person who scored high on Fawcett's measure of ethical idealism and person who did not score high on that instrument. For 91 non-idealists, the correlation between misanthropy and support for animal rights was 0.3639. For 63 idealists, the correlation was 0.0205. The test statistics have been calculated, Z equal to 2.16 with a p-value of 0.031, leading to the inference that the correlation in non-idealists is significantly higher than in the idealist. Let us take up a numerical example and explore the discussed concept in a more applied way and compute the differences. A researcher predicts that the adults have a more accurate idea of failure at a task than teenagers. To gather the data, a task was explained to a group of adults and a group of teenagers with sample size equal to 30 in each case. They were also asked to perform the task and measures of success and failure were obtained. The idea of possible failure and actual failure of the task was correlated. The correlation for teenagers turned out to be 0.50. For the adults, this correlation coefficient was found to be 0.80. As the researcher also wished to compare the teenagers and the adults in their potential to predict the failure more accurately, the difference between the two correlation coefficients was put to significance test. We have already discussed the steps and concepts involved in testing of this difference between two correlations for independent samples. Let us proceed with this data and compute the results for the null hypothesis. A one-tailed directional alternative hypothesis was formulated and it was tested at 0.05 level of significance. So, the null hypothesis states that rho for adults is equal to rho for teenagers. That is, the correlation of adults and correlation of teenagers were converted into their Z value using Fisher's equation. The values are also available in statistical tables meant for the purpose. However, the readers will remember that we have already discussed this equation in the previous section. So, we calculated the Z after the transformation on Fisher's equation, and using the formula, the Z value is found using the equation Z is equal to R adults minus R teenagers divided by square root of 1 minus N adults minus 3 plus 1 upon N teenagers upon minus 3. After Fisher's transformation on the correlation coefficients and substituting the data from the stated research problem, the equation is now as follows, and the Z value turns out to be 2.02. When one looks up the one-tailed probability of this Z calculated value in the table of area under the normal curve, the probability of 0.0217 shows that the null hypothesis of no difference between the correlation coefficients is rejected, and the adults do have a better and accurate idea of failure at a task than the teenagers. Studying the statistical significance of difference between two correlations in dependent samples. Dependent samples. Dependent samples are paired measurement of one set of items. So, in dependent sample, each observation in one sample can be paired with an observation in the other sample. The following sample could be collected on the same group of units or individual. At the two different points in time, for instance, responding to the same question at 2 points of time. For two different items, for instance, responding to different questions. Responses from such dependent samples are statistically dependent. For instance, if a drug company wants to test the effectiveness of a new drug in reducing blood pressure, a dependent sample based data collection would include sampling the blood pressures of the same people before and after they receive a dose. The two samples are said to be dependent because they are taken from the same people, and the persons with the highest blood pressure in the first sample is likely to have high blood pressure in the second sample also. So, we see that the observations in both the samples are dependent on each other. The steps in making a comparison. The steps discussed are applicable to the situation when one has three variables like x, y and z, and one wishes to compare the x to y correlation with the x to z correlation. It is used when one wants to know which of the two variables are more related to the third variable. Also, if these relationships are significant statistically. So, in order to test if differences exist in correlations from two dependent bivariate populations from which the samples are drawn, the following hypotheses may be tested. You see the hypotheses which are mentioned here, where rho 1, 2 and rho 1, 3 are the population correlations from which the samples were drawn. This testing has certain assumptions to it, and the first assumption is that the samples have been randomly drawn from two dependent bivariate two-dimensional population. The populations may be modeled with a bivariate normal distribution, and the correlations represent the degree to which a linear relationship exists between the two variables. The correlational matrix is obtained by applying the Pearson's product moment correlation to the data for all the variables, and the table represents the correlation matrix of the three variables. You can see the correlation between variable 2, 1, 3, 1 and 3, 2 are shown there. So, if one wishes to compare the correlation between variables 1 and 2 with that of variables 1 and 3, the steps taken would be like this. First, we calculate the determinant of the correlational matrix, which is modulus of R, where R represents the determinant as 1 minus R correlation between 2 and 1 minus R31 minus R32 plus 2 into R21 into R31 into R32. Of course, R is the determinant of the matrix and it is a modulus always of the matrix, and the R values are the correlation coefficients. We also compute the mean of the two correlations to be compared as mean R is equal to R21 plus R31 divided by 2. We find the t value with degree of freedom n minus 3, where n is the sample size. The test statistic henceforth applied is t is equal to the following: R12 minus R13 into the square root of n minus 3 into 1 plus R23 divided by 2 into 1 minus R square 23 minus R square 12 minus R square 13 plus 2 R23, R12 and R13, where t has n minus 3 degrees of freedom. Once the t obtained is there, we compare it with the t critical value obtained from the table according to the degree of freedom and the alpha value that we have already decided, and we establish the significance of the difference. Let us use these concepts now and see how they can be applied to the data by picking up a numerical example. Let us take an example. A researcher gives IQ test to 20 couples. The eldest son of each couple is also given the IQ test with scores displayed in the table. As 20 couples were taken, the data is for all the 20. The researcher wishes to know whether the correlation between the son and the mother is significantly different from the correlation between the son and the father. The following test statistic will be put to use. T is equal to the following equation, where S is 3 into 3 sample correlational matrix and its determinant is calculated using the equation. We have already discussed these two things in the previous section. The results of the above data that we have in the table for the 20 couples and their son is used, and we substitute the values in the equations that we have just discussed. The result for the is displayed where the upper part of the figure contains the correlational matrix also. Now, since the p-value of 0.042 is less than 0.05, that is the alpha value, or t obtained is less than the t critical, the researcher rejects the null hypothesis and concludes that the correlation between the mother and son is significantly different from the correlation between father and the son. Summary: After establishing a relationship between the two variables or measures through correlation, the next inquisition is to know if this correlation coefficient is significant enough or not. The steps involved in testing the significance of correlation coefficients are discussed in the text. The application of the t-test in testing the significance of correlation is done. The steps involved obtain the calculated and critical t-values are also there, and the conclusions are made accordingly. The independent samples are samples selected from the same or different populations which have no effect of each other. No correlation exists between the samples. For instance, when one wishes to know whether height and weight are correlated in the same way for two distinct social groups. The steps in making comparison between the correlation coefficients obtained from independent samples are explained. The assumptions for testing are discussed. The samples have been randomly drawn from two independent bivariate two-dimensional population, and the populations may be modeled with a bivariate normal distribution. The correlations represent the degree to which a linear relationship exists between the two variables. The significance assessment steps are discussed in the test, and the numerical application of these concepts has also been taken up to explain them. The dependent samples or the paired measurement of one set of items. So, in independent samples, each observation in one sample can be paired with an observation in the other sample. Steps in making a comparison between the correlation coefficients obtained from the dependent samples are explained. The assumptions required for the test are discussed, as the samples have been randomly drawn from two dependent bivariate two-dimensional population. The populations may be modeled with a bivariate normal distribution, and the correlations represent the degree to which a linear relationship exists between two variables. For the dependent case, Fisher's Z transformation for correlation coefficients followed by testing of the null hypothesis rho 1 minus rho 2 equal to 0, and using the student's t-test has been taken up, followed with a numerical example that explain the computational steps involved.